All right, this next section, we're going to just talk about allylic radicals. So last examples were allylic carbocations. This is allylic radicals, and you know what? Nothing is changed. It's the same concepts. You have a radical next door to a pi bond, and because of resonance, it's stabilized, and you can do radical reactions. Okay, so stabilized by resonance. Okay, radical stability is just like what we've seen. All right, primary is less stable than secondary, less stable than tertiary, and then you got your allylics, which are more stable than your tertiary because of resonance. All right, the substitution at the allylic position competes with the addition to a double bond. Okay, that is kind of like the difference here. Is that if you're doing a reaction, you might have a reaction at the double bond rather than at the radical. Okay, but usually it does happen at the radical. All right, to encourage a substitution, you use a lower concentration of reagent with light, heat, or peroxides to initiate free radical conformation. So remember, if you want to do radicals, you have to initiate it. Okay, so you just use less amount of radical formation compound. Okay, so that's kind of how you do it, but that's more of a experimental method. So just to remind you what the mechanism is for radicals is you have an initiation step, which is breaking of your bromine, which is not the important step, it's the propagation. That's the important step. Once you form your radical, remember it resonates. Remember the arrows for radicals are half-headed arrows. So this electron, all right, pairs up with one of the electrons from here, and then the other electron, the second electron in the pi bond, goes to there, which gives you that compound. So this electron plus one electron here come together, and then the one left electron here stays on the carbon up there. All right, so it's resonating around. Your bromine then is able to attack one of the radicals to form your product. Okay, now a very useful reagent is NBS. If you want to brominate allylic or at the benzylic position, NBS is a great reagent. Okay, this is the structure of NBS right here. All right, NBS is a shorthand for N-Bromosuccinimide. All right, obviously with the N we'll learn about how to name nitrogen-containing compounds. But anytime you have something hanging off of a nitrogen, you always say N followed by what's hanging off of it. In this case, it's a bromine. If it was a methyl, it'd be N-methyl-succinimide. But you have a bromine, and then this group, this 5-membered ring with the nitrogen, is called succinimide. It's just a common name here. It's actually right here with the hydrogen. All right, so that's NBS. It's used as an allylic bromination. It prevents adding two pi bonds. Like I said, if you add bromine in a radical, you can actually add bromine to the pi bond rather than adding it to the radical. So NBS provides a low concentration of bromine. Okay, so the NBS reacts with the HBr byproduct to produce bromine and to prevent HBr addition across a double bond. So that's the whole point. It's to prevent this formation of HBr. Okay, the allylic system, very similar to that we've already seen. It's you've got your pi bond. All right, let's say here's your pi bond right here. All right, and you have your radical. So let's say it looks like this type of a compound. All right, well, this is in a pi bond. That radical is in a pi bond, and a pi bond here, and a pi bond here, and that radical is resonating through the whole thing. So that's what this picture is showing you. It's showing you that you have the overlap. Okay, so geometric structure of the allyl cation, allyl radical, and allyl anion. So that's basically a general structure for all of them. It doesn't matter if it's a radical, a negative charge, or a positive charge. All three pi orbitals are in the in the pi system, and you got this overlap between the C1, C2, and the C2 and the C3. So that's an Allyl system. It doesn't have to be a radical. So allyl could be radical, it could be a negative charge, or it could be a plus charge. This is what's implied by an Allyl system. Allyl meaning allylic system. Okay? Again, are you guys getting sick of seeing resonance stabilization yet? All right, if you're not, you're going to probably see it 27 more times. I'm just kidding. Anyways, the whole point is resonance stabilization. Okay, and here's again another perfect example of kinetic versus thermodynamic controlled. All right, this is the much more stable intermediate because it's secondary radical. This is a less stable intermediate because it's the primary, but the double bond is more substituted. Okay, so kinetic, thermodynamic. Notice you get two different products. If you want to favor this product, okay, think about it. That's the kinetic product. So what kind of conditions? Cold temperatures. This is the thermodynamic product because you have the much more stable product. You do this under, you warm it up. Okay? So let's see what this says. Even though this slide's not about that, just want to review. During propagation, an allylic radical is formed that is stabilized by resonance. We know this. Either radical can form product. Okay, unless you change the conditions. You cool it down or heat it up or do whatever you need to do. Okay? Allylic anions, same type of thing. They're just going through each individual thing. The allylic anion has 2 electrons in the pi molecular orbital. Don't worry about the pi 2, but MO stands for molecular orbital. So you actually have a molecular orbital here. It's not a p orbital. It's a molecular orbital, meaning it's a hybridized orbital. That resonates, same type of thing. As with the allylic cations and radicals, the allylic anion is also stabilized by resonance. Okay, nothing too fancy. 15.2 just talks about that you can actually do SN2 reactions on allylic halides and on the tosylate. Okay, so if it's allylic, and these reactions occur much faster. Okay, so if you just had a regular, let's say SN2 with a bromine here, and you adding hydroxide to it, all right, to form that, versus if you have this and you add hydroxide to it to form, sorry, I'm running out of space here. Oh, got an extra carbon in there. This system will go much faster because again you have a stabilized carbon here. There's much more partial positive character there than there is compared to here. So if you had both these things mixed together, your hydroxide would most likely go and attack here because you have a much more partial positive charge on that allylic. All right, so SN2s occur the same way, backside attack, but much faster on the allylic molecules. Okay, the transition state of the SN2 mechanism is stabilized through conjugation with the p orbitals. This transition state has a lower activation energy. Remember, lowest activation energy means faster. All right, and explains the enhanced reactivity of these allylic species. So basically what I talked about. So here's an example of nucleophilic attack on just a regular propyl group. All right, here it is on an allyl group. It's kind of showing you that this that the orbital that the bromine is in is stabilized. Okay, don't worry too much about that. I just want you to understand the partial positive. They don't really say it. The book doesn't really say it, but that's what's going on. You basically have a much larger partial positive charge on this carbon compared to this one. I'll put a little partial positive, right? So this bond between your carbon and bromine is much longer. This bromine kind of already wants to leave. It's just hanging on there by a thread. It's just barely hanging on. It needs something, and something, boom, comes in and it goes. This bond is much stronger. It's not as long, okay? Because that bromine, this carbon would be a primary carbocation. It does not want to be a primary carbocation. These don't become cations because it's SN2, but you can look at it as if it's on the way of wanting to leave. So again, it's partial charges. It's not full-fledged charges. Okay? So now the other thing is, this is something very interesting. You can do SN2 reactions with organometallics on allylic compounds. All right, you cannot do this before. So if you had a Grignard, let's say you have methyl Grignard, all right, we learn that you have to add this to some sort of carbonyl compound. Okay, I'll put an H there. Either a ketone or an aldehyde. All right, so that the Grignard comes in and attacks there and it kicks up your pi bond. That's what we learned. I believe I told you, or the book told you, is that you cannot just do a general SN2 reaction. If you were to take a Grignard and add it to some sort of alkyl-halide, all right, to have the methyl just attack the carbon and kick out the chlorine, all right, to form methane in this case. I taught you that this does not occur. All right, Grignards only attack carbonyl compounds unless it's allylic. Okay, so now I can do SN2 reactions with allylics. I'm sorry, with either organolithiums or Grignards, as long as the alkyl halide is allylic. All right, again, it's the same type of special case. This charge is stabilized in the pi bond, much bigger partial positive. Your Grignards are actually able now, or your organolithium can now attack your carbon and kick out your bromine. Only on allylic systems, not on, otherwise they have to be pi bonds. You got to attack the actual pi bond. Now, note that this is not attacking the pi bond, it's attacking the carbon to it. Okay? Sorry, I went backwards. And that will be the end of the discussion, and we will pick up 15.11 and the Diels-Alder reaction on the next videos.